Welcome to the deep dive. You, our listener, with that insatiable curiosity, you've pointed us right at the core today. The official Postgresql version 17.4 documentation.
hmm
Think of this as your streamlined guide. We want to unlock the essential power of Postgres for you.
Yeah, our mission is pretty straightforward, really. We're here to pull out the crucial bits, those aha moments that actually help you understand things.
Without getting totally lost in the weeds, right?
Yeah.
Because that documentation is, well, it's huge.
It is. And our journey today, it draws straight from that 17.4 doc. We'll be looking at, how you define data structures, the amazing variety of the data types you can use,
Okay.
and the basics of just getting a Postgres server up and running, configuration, all that.
And backups. Can't forget backups.
Definitely not. Backups, restore, high availability for uptime, the SQL language itself, which is, fundamental.
Of course.
Plus the massive toolkit of functions and operators, making text searchable with full text search, handling multiple users at once, concurrency.
How it optimizes queries.
Exactly. Query planning, monitoring the system, maintenance routines, adapting it for different languages, localization stuff,
How your apps actually connect.
client interfaces, yeah. And even a peek at the testing that makes Postgres so reliable. It's quite a comprehensive trip we're taking.
It really is. And, diving in, a couple of things jumped out at me immediately. First, that version number, 17.4.
Right.
It just screams history, decades of development, makes you think about why staying current is, well, pretty critical.
Absolutely. The docs even hint at that. Older versions might get limited support.
So upgrading is usually the move for bug fixes, performance boosts, all that good stuff.
And that long history means they've seen a lot, solved a lot of problems.
Mhm.
All that knowledge is packed into the documentation.
Which explains why it's so big. It can feel a bit like climbing a mountain at first.
For sure. But our goal here is to sort of map out the key trails for you. Make it manageable. Make it useful.
And the second thing I noticed, right there in the docs, a tutorial section.
Oh, yeah.
That really clicked with, the whole learner persona we're thinking about. It shows they want people to learn it.
It does. A focus on accessibility, which lines up perfectly with what we're doing, aiming for that practical understanding of the key parts.
Okay, let's do it. Let's unpack this, starting right at the beginning. How do we actually define the structure for our data?
Right. So first steps in any database project usually involve defining your tables. And the command for that, no surprise, it's create table.
Okay, standard stuff.
Pretty standard. You need, at minimum, a name for your table, and then for each column, you need a name and a data type. What kind of data will it hold?
Like a products table with a name column that's text and a price column that's a number.
Exactly like that. And crucially, right when you create the table, you can also set up rules for that data. These are called constraints.
Constraints. Okay, the rules to keep the data clean.
Right.
And the docs highlight something called generated data as identity. That sounds useful for automatic IDs.
Oh, incredibly useful. It gives you those auto-generated, always unique identifiers for each row. You don't have to manage them yourself.
And it mentioned options like always and by default. What's the difference there? When would I use which?
Good question. Think of generated always as the really strict one. Postgres generates the ID, period. You can't insert your own value. Grubs are things like audit logs where you absolutely need system control.
Okay, ironclad uniqueness.
Right. Generated by default is more flexible. Postgres will generate an ID if you don't provide one when you insert a row.
Ah, so I can override it if I need to.
Exactly. Useful if you're maybe importing data that already has IDs, or you have some specific reason to assign one occasionally.
Got it. Always for strict, by default for flexible. And then the regenerative columns, too.
Yeah, those are neat. Columns whose values are automatically calculated from other columns in the same row.
Oh, like having quantity and unit price columns and a total price column that just multiplies them.
Precisely. Keeps things consistent automatically. No need to calculate it every single time you insert or update.
Nice. Okay, back to those other constraints. You mentioned them earlier. Things like unique, not null, and the big one, primary key.
Exactly. Unique ensures no duplicate values in a column or set of columns. Not null means a column must have a value. It can't be empty.
Standard database stuff.
Pretty standard. And the primary key is a main unique identifier for a row. The docs make a key point here. Defining a primary key automatically creates an index on it.
An index for performance.
Yes, usually a B-tree index. Makes looking up rows by their primary key super fast. And then to link tables together, we use foreign key constraints.
Using the references keyword, right?
Right, that's how you build relationships. It enforces referential integrity.
Making sure, like, every order in an orders table actually points to a real customer in the customers table.
Exactly. You can't have orders for non-existent customers. It keeps the data consistent across tables.
Okay, so foreign keys are the glue holding related data together. We've created tables, set constraints, but what if things change? We need to modify them later. Alter table comes up.
Alter table is your go-to. It's super versatile. You can add columns, drop columns you don't need anymore, change a column's data type.
Add or remove constraints.
Yep. Add or remove unique, not null, foreign key, check constraints, all that. The docs even call out dropping not null specifically.
Oh, why is that special?
Because not null constraints don't usually have explicit names like others. So you can't just say drop constraint name. You have to use your cat table, alter column, your column, drop not null. A slightly different syntax to remember.
Good tip. And you can change default values too.
Yeah, alter table will call set default. So new rows get that default if you don't specify a value.
Makes sense. Now, the docs mentioned something more advanced for access control. Row security policies. When would you use those?
Row security policies, or RLS. They're really powerful for fine-grained access control within a table. Imagine a multi-tenant app.
Where different customers share the same tables.
Exactly. But customer A should only see their data, not customer B's. RLS lets you define policies, usually based on the user's role or maybe a tenant ID column, that filter rows automatically.
So the database itself enforces who sees which rows.
Precisely. It's a strong security feature baked right in. Then, related to organization, we have schemas.
Schemas, like
Yeah.
logical folders inside the database for organizing tables and views and stuff.
That's a great way to think about it. Namespaces, folders, they keep things tidy, prevent naming conflicts.
And the documentation talks about the search path. How does that work with schemas?
The search path is basically a list of schemas Postgres checks, in order when you refer to an object like a table without specifying its schema.
So if I just type select from customers.
Postgres looks in the first schema in your search path. If you find customers there, great. If not, it checks the second schema and so on.
And where do new tables go if I don't specify a schema?
They go into the first schema listed in your search path, which is called your current schema. By default, the path often includes user, a schema named after you and public, the default schema everyone can usually access.
Okay, so search path controls where Postgres looks for things and where new things land by default. Clear. Now, things got interesting with inheritance and table partitioning. Both sound like ways to handle really big tables.
They are, but they work differently, and partitioning is generally the way to go these days. Inheritance lets you create child tables using inherits. They automatically get all the columns for the parent table.
So you can query the parent and get data from all the children too?
Yep, by default. But the docs point out limitations. Things like indexes or check constraints on the parent don't automatically apply to the children. It can be a bit fiddly to manage.
Right, sounds like it could get messy. So partitioning is the preferred approach. How's that different?
Partitioning is much more structured, especially the declarative partitioning introduced in newer Postgres versions. You define a main table, the partition table, and then rules for how data gets split into child tables, the partitions.
Split based on what?
Could be ranges of dates, lists of specific values like regions, or even hash values. The big win is partition pruning.
Partition pruning.
Yeah, the query planner is smart enough to look at your query's where clause and figure out which partitions actually contain the data you need. It only scans those, ignoring the rest.
So if I query for orders in January, it only looks at the January partition, not the whole year's worth of data.
Exactly. Huge performance boost for large data sets. There are stricter rules than inheritance, though. All partitions must have the exact same columns as the parent. You can't mix temporary and permanent tables in a partition set. It's more robust, more managed.
Declarative partitioning sounds like the way forward for big tables then. Much smarter query execution. Lastly, in this data definition part, foreign data. Accessing data outside Postgres.
Yep. Foreign data wrappers, or FDWs. They let you connect to external data sources, other Postgres databases, MySQL, Oracle, even flat files or web services, and query them like they were local tables.
Wow. Okay, so you can integrate data without moving at all.
Exactly.
Yeah.
Super powerful for data integration scenarios. Okay, so we know how to structure data. Now, what kind of data can we actually store? Postgres has an incredibly rich set of data types.
It really looks like it. The basics are there. Integer for whole numbers. But then numeric, that sounds more precise. It mentions precision and scale.
Numeric is your go-to for exactness. Think money, financial calculations, anything where you absolutely cannot tolerate rounding errors like you might get with floating point types.
So I can say I need exactly 10 digits total with 2 after the decimal point.
Precisely. You define the precision, total digits, and scale, digits after decimal, and it stores it efficiently, only using the space needed. For science or engineering, where speed might matter more and slight approximation is okay, you'd use real or double precision, the floating point types.
Okay, numeric for money, floats for science. Makes sense. For text seems like the main one for variable length strings.
It generally is the most flexible and commonly used text type, yeah.
Then time. Date, time, timestamp. And timestamp can include time zone info or not. That time zone part seems crucial for global apps.
Absolutely essential if you're dealing with data across different regions. Timestamp with time zone stores the timestamp in UTC internally and converts it to the client's session time zone on retrieval. Timestamp without time zone just stores the literal date and time you give it.
And the docs warned against using literals like tomorrow in the database, right? Use SQL functions instead.
Yes, very important warning. Tomorrow depends on when you ask. Storing it is ambiguous. Functions like current date, current timestamp now are evaluated at execution time. They give you the actual current time, which is what you usually want to store.
Good point. And there's interval, too, for durations.
Yeah, interval is great for storing time spans like 3 days, 4 hours, or 6 months. Very flexible input and output formats.
Then the simple Boolean for true-false. And enum types looked interesting custom lists of allowed values.
Enums are fantastic for data integrity. Define an order status EMM with values like pending, shipped, delivered. Then the database only accepts those values for that column. No typos, no weird entries.
Makes the data much cleaner.
Much cleaner and more self-documenting. Plus, they're type safe. You can't accidentally compare an order status enum with, say, a shipping method enum. We also get brief mentions of specialized types like geometric for 2D shapes, network address for IPs and CIDR blocks, bit string for raw bits.
Newer niche stuff?
More niche, but powerful if you need them. Then text search types. Teasvector and Sciri. We'll definitely circle back to those later for full text search.
Okay, UID for universally unique IDs, good for distributed systems.
Essential for that, yeah. Guarantees uniqueness across different databases or systems.
And native support for XML and JSON. That's huge nowadays. How do JSON and JSONB differ?
Big difference in practice. JSON stores the JSON text exactly as you give it. It has to reparse it every time you query.
Okay, so maybe slower.
Can be, especially for complex queries. JSONB stores it in a decomposed binary format. It parses it on input, which takes slightly longer, but querying is much faster.
And you can index JSONB effectively.
Yes, that's a major advantage. JSONB also removes insignificant whitespace and duplicate keys and doesn't preserve key order. For most use cases, JSONB is the one you want because of the performance and indexing.
And there's JSON path for querying inside JSON.
Right, a standard way to specify paths into JSON documents, used with various JSON functions and operators like nests and meth to extract data.
So JSONB for performance and features generally. What about arrays? Postgres seems to handle those well too.
Very well. You can have arrays of almost any data type, even multi-dimensional arrays. Store a list of tags, phone numbers, whatever fits. Lots of built-in functions to manipulate them too.
Like adding elements, getting the length.
Appending, concatenating, slicing, checking for containment, converting to strings, finding dimensions, cardinality, array length, aggregating rows into an array ag. It's quite complete.
And composite types. Sounded like creating your own mini structures.
Kind of, yeah. You define a type with named fields, like a struct in C or an object. You can then have a column of that type, holding multiple related values together, like a point with an X and Y coordinate.
And you access the fields with dot notation, like myPoint.x.
Exactly. The docs mention the optional ROW keyword when creating composite values like ROW1, ABC, but often it's inferred.
Okay. Then range types, representing intervals, like a date range for an event.
Precisely. Date ranges, numeric ranges, timestamp ranges, super useful. Postgres provides special operators to check for overlap, containment, adjacency, plus functions to get the upper and lower bounds. Check if they're inclusive, uppering, or infinite lower, up and imperative, or if the range is empty, is empty.
And aggregate functions to combine ranges?
Yep, like ranged to merge overlapping ranges. And there are even multi-range types to store collections of non-overlapping ranges.
Wow, okay. It feels like there's a type for everything. We still have domain types and object identifier types.
Almost done. Domain types let you create a custom type based on an existing one, but add constraints, like an email domain based on text, but with a check constraint to validate the format. Enforces rules at the type level.
Another integrity booster.
Exactly. And object identifier types, or OIDs, are internal members Postgres uses to identify objects like tables, functions, types. You don't usually use the raw OIDs directly.
But there are aliases, like reg class.
Right, reg class, reg proc, reg type, etc. These let you refer to objects by name, optionally schema qualified, like public.customers. And Postgres converts it to the internal OID, much more readable in queries or system functions.
And pseudotypes.
Those aren't types you can use for table columns. They're special markers used internally, like the return type for functions that don't return a specific value, void, or for defining polymorphic functions, inch element.
Okay, what a tour of data types. So we know how to define tables and what data they can hold. Now, getting the server actually running, server administration, starting with installation. Binaries versus source code.
Binaries are usually easier, quicker. Use your OS package manager, apt, yum, brew, or the official installers. Done.
But source code gives more control.
Yeah, if you need custom compile options, the docs mention the .configure script with flags. Maybe you need specific SSL support or GSS API for Kerberos, or maybe enable compression libraries like LZ4 or Z standard.
Advanced stuff.
Mostly advanced stuff. Or if you need a feature not in the standard binaries, you can enable dtrace for deep system tracing, things like that. Then it's the usual make install.
And after installing the files, the crucial step is initdb, right? To create the actual database cluster.
Absolutely critical. initdb sets up the data directory where all your tables and data will live.
Yeah.
It creates the system catalogs, default config files, and importantly, sets strict file permissions on that data directory.
For security, only the Postgres user should touch those files.
For sure. Then you start and stop the server, typically using pgctl.pgctl start to dpath the data-l log file to start it up, pgctl stop to shut it down cleanly.
And the docs mention common connection issues, firewalls, listening addresses.
Yeah, classic beginner hurdles. Is the server actually listening for network connections? Listen addresses in postgresql.conf. Is the firewall blocking the port, default 5432? Are the authentication rules in pghba.conf set up correctly?
Okay, server installed, running, now tailoring it. Server configuration. The main file is postgresql.conf, right? But there are other ways to set parameters.
Postgresql.conf is the primary place, yeah. Huge file, tons of options. But you can also set parameters. 1, on the command line when starting Postgres, less common. 2, per session using the SQL set command, changes only last for that connection. 3, persistently using alter system set parameter equals value. This writes to postgresql.auto.conf and overrides postgresql.conf. Requires a reload or restart depending on the parameter.
And not all parameters can be changed on the fly. Some need a server restart.
Correct. Major things like shared buffer size usually require a restart. Many others just need a configuration reload, which you can trigger with pgkeel reload or the SQL function pro loadconf. Much less disruptive.
Good to know. The config section breaks down parameters by area. File locations is obvious. But connections and authentication, that seems fundamental.
Absolutely foundational. Max connections limits how many clients can connect simultaneously. Tune that based on your app and server resources.
Listen addresses controls which network interfaces it listens on, like just local host or all interfaces.
Exactly. For all or specific IPs for tighter security, port is the TCP port 5432 default. Unisocket directories for local connections via sockets.
And authentication methods, lots of options there.
A whole range in pghba.com/trust. Dangerous, avoid unless you really trust the network OS security. Password methods, MD5, the more secure Scramshot 256. Kerberos, Saccaberos, Windows, SliveDAP, Radius, certificates, CERT, system authentication, PAM, BSD, Identit. You configure rules based on user, database, and connection source address.
And SSL/TLS for encrypting connections.
Essential over networks. Enable with SSL on in postgresql.com. Point to your server certificate and key seller's file, logos file, and optionally a CA file, Celca file, if you're doing client certificate off.
Security first. Okay, next big area, resource consumption. Managing memory, CPU usage, parameters like shared buffers, workmem. Those sound important for performance.
Very important. Shared buffers is the main memory cache for data blocks read from disk. Bigger can be better, reduces disk I/O. But don't starve the OS. Maybe start around 25% of system RAM and tune from there.
And workmem, that's for sorts and hashes.
Right. Memory use per operation within a query, sorts, hash, joins. If you have complex queries, increasing it might help them run faster in memory instead of spilling to disk. But beware.
Why beware?
Because it's per operation, per connection. If you have 100 connections all doing complex sorts, a high workman can quickly exhaust your server's RAM. Start low, increase cautiously.
Okay. And maintenance work mem is similar, but just for maintenance tasks.
Yeah, things like vacuum, create index, alter table, add foreign key.
Hmm.
These often benefit from more memory, and since they run less frequently than user queries, you can usually set this much higher than workmem safely.
What about parallel workers?
Max parallel workers. Max parallel maintenance workers control how many background processes can be used for parallel query execution or parallel maintenance. More workers can mean faster complex queries if you have the CPU cores.
And effective cache size. It doesn't allocate memory.
Correct. It's just a hint for the query planner. It tells Postgres how much memory it thinks the operating system is using for its own file system cache, plus Postgres's shared buffers. A higher value makes the planner more optimistic about finding data in cache, potentially favoring index scans over sequential scans. Setting it realistically helps the planner make better choices.
Got it. Now, a really critical part for reliability, the write-ahead log, or WAL. The docs stress its importance for recovery. Parameters like wall level, synchronous commit. What's the deal with WAL?
WAL is the absolute cornerstone of Postgres durability. Before any change hits the main data files, it's written sequentially to the WAL logs, like a journal.
So if the server crashes,
On restart, Postgres replays the WAL logs from the last checkpoint. It reconstructs the state of the database up to the point of the crash, ensuring no committed transactions are lost.
okay. And wall level controls how much gets logged.
Exactly. Minimal is just enough for crash recovery. Replica, or logical in newer versions, adds info needed for streaming replication and logical decoding.
And synchronous commit. That sounds crucial for transaction safety.
It is. It controls when Postgres reports commit successful back to the client. On the default means it waits until the WAL record for that transaction is safely written to durable storage on the primary and any synchronous standbys, if configured. Maximum safety.
But maybe slower.
Potentially adds latency, yes, you can relax it.
Yeah.
Local waits only for the write on the primary's disk.
Mm-hmm.
Off, asynchronous commit, doesn't wait for the disk write at all before acknowledging the commit.
That sounds risky.
It is. You trade performance for a small window of potential data loss if the primary crashes immediately after acknowledging the commit, but before the WAL hits the disk. The docs strongly advise against disabling Finc altogether, but asynchronous commit, synchronous commit off, is a less extreme performance tuning option if you can tolerate that small risk.
Okay, so on is safest, off is fastest but riskier, and there are intermediate levels for replication too.
Yeah, remote write waits for standby to receive and write WAL, and remote apply waits for standby to receive, write, and apply WAL. Gives you fine-grained control over synchronous replication guarantees.
And wall archiving, archive mode, archive command, is for point-in-time recovery.
Exactly. Continuously copying those completed WAL segments somewhere safe allows you to restore backup and replay logs to recover to any specific point in time before disaster.
Okay, wall is fundamental. The config section goes on forever, covering replication, query planning hints, default statistics target, random page cost, logging, log destination, log statement, error handling, even debugging flags. It's incredibly tunable.
It really is. You can control almost everything.
Yeah.
Which leads us to protecting all this data, backup and restore. The docs cover two main ways: logical backups with pgdump and file system level backups.
pgdump seems pretty standard. Creates SQL scripts or archive files.
Yep. Very flexible. Good for migrating, restoring specific objects. Works across versions usually. Can run in parallel, BGJ to speed things up. Different archive formats: BGFUF, KiriaC for custom, TacuC for tar.
And file system backups, just copying the data directory.
Physically copying the files.
Yeah.
But if the database is running, you must use PG start backup before you start copying, and PG backup stop when you're done.
Why is that absolutely necessary?
Because the files on disk might be in an inconsistent state at any given moment while the server is live. PG start backup tells Postgres, hey, a backup is starting. It forces a checkpoint and ensures all subsequent WALs contains enough info to make the copied files consistent when you eventually restore and replay the WAL generated during the backup. Skipping this makes the backup potentially unrecoverable.
Okay, crucial steps for physical backups. And then there's continuous archiving and point-in-time recovery, PITR. That sounds like the ultimate safety net.
It really is. You enable archive mode, set up an archive command to copy WAL files somewhere safe as they fill up. Then, if disaster strikes, you restore your latest base backup, physical or logical, and tell Postgres to replay the archived wall files.
And you can stop at a specific time, like right before someone dropped a table.
Exactly. Using recovery target time or recovery target exit, transaction ID, or other targets in your recovery configuration, it lets you wind back the clock with minimal data loss. Recovery and command can run cleanup scripts afterwards.
So backups are essential. PITR is the time machine. Got it. Now, keeping the database available, high availability, load balancing, and replication. Lots of approaches mentioned.
Yeah, the docs give an overview. Shared disk, less common now.
Hmm.
File system replication, usually bad for live databases. Wall shipping, very common. Logical replication, more flexible replicates logical changes. Older trigger-based methods, middleware for failover, even multi-master setups.
But wall shipping seems key. Log shipping standby servers. Setting up replicas that get wall from the primary.
That's the core idea. A standby server connects to the primary using primary coninfo and streams wall records as they're generated. It then replays those wall records to keep its own data copy almost up to date.
And replication slots help with this, using primary slot name.
Replication slots are a big improvement for reliability. They are created on the primary for a specific standby. The primary promises not to remove any wall files until the standby connected to that slot confirms it has received them.
Ah, so if the standby disconnects for a while, the primary won't discard wall files the standby still needs.
Exactly. Prevents the standby from falling too far behind and needing a full resync. Much more robust.
Makes sense. And hot standby means you can run read-only queries on the standby while it's replicating.
Yep. Great for offloading read traffic from the primary. Failover is the process of promoting a standby to become the new primary if the old one fails. Cascading replication lets a standby feed wall to other standbys, reducing load on the main primary.
And synchronous replication, that ties back to synchronous commit.
It does. You list standbys in synchronous standby names on the primary. If synchronous commit is on or remote write or remote apply, the primary waits for confirmation from at least one of those synchronous standbys before confirming the commit to the client. Highest data durability guarantee across servers.
All these features really lean on reliability and the write-ahead log. The docs mention data checksums, too, for detecting corruption.
Yes, an optional feature you enable when you init DV. Postgres calculates a checksum for each data block when it's written. When it reads the block later, it recalculates and compares. Mismatch means corruption.
And it warns heavily against ignore checksum failure.
Very strongly. Ignoring checksum failures means you're potentially reading and using corrupted data without knowing it. Hugely dangerous. Never turn that on in production. The Golden Wall, as we said, is key for recovery. An asynchronous commit is the safer way to trade some durability for performance, much better than disabling vsync entirely.
Okay, reliable, available system. How do we use it? The SQL language starts with the basics. Create table, insert, select, update, delete.
The bread and butter, DDL, create, and DML, insert, select, update, delete. Then select deep dive from clause for tables, where for filtering rows.
Coining tables, inner join, outer join.
Right. Inner join for matching rows in both tables. Left, right, full outer join to include rows, even if they don't have a match in the other table. You specify the join condition with on, or using if the joining columns have the same name.
Aggregate functions. Count, sum, evg, min, max for summarizing.
Essential for reporting. Docs note they usually ignore nulls. Distinct keyword to aggregate only unique values. Group by clause is key here. Groups rows with the same values before aggregation.
And having filters after grouping.
Exactly. Where filters rows before grouping, having filters the grouped results after aggregation. Subtle but important difference. Then order by to sort results, limit and offset for pagination.
Views create virtual tables from queries.
Yep. Saved queries that look like tables. Great for simplifying complex logic or restricting access to certain columns rows. You can often use them just like real tables.
Foreign keys revisited the SQL syntax for creating those links. And operators, comparison, logical, string concatenation, etc.
Lots built-in operators. Docs mention rules for multi-character ones and operator precedence, order of operations.
Window functions looked powerful, calculations across related rows without collapsing them.
Super powerful. Think running totals, rankings, rank, dense rank, comparing a row to the previous row, lag, led. Use over, partition by, order by, to define the window of rows the function operates on for each row.
Different from aggregates which squash rows down.
Totally different. Then typecasts for explicit convergence, cast x as integer, or the shorthand x.integer. Common table expressions, CTEs, with the with clause.
Those let you name temporary results within a query, make complex queries readable.
Exactly. Break down complexity. With my temp result as, select from my terms result.
Mm.
Also enables recursive queries for hierarchical data, org charts, parts explosions.
Values lists for specifying literal rows, and advanced grouping like rollup, cube, grouping sets for multi-level totals.
Yeah, concise ways to get subtotals and grand totals in one go without multiple queries or complex unions.
SQL is powerful, but functions and operators add so much more. Numeric functions, abs, round, seal, floor. String functions, substring, trim, lpat, length, hashing like MB5 shade 256.
A huge library. Concatenation, finding position, replacing parts, encoding, decode, Unicode normalization, regular expression matching for case-insensitive, and functions rejects places retotable.
Datetime functions, age, date, trunk, now, current date, time zone conversions. Geometric functions, XML functions, XML parse XPath, JSON functions and operators, XML plus XPath.
Tons for JSON, JSONB manipulation and querying. Array functions, array append, array length, unnest, composite type access, dot notation, range, multi-range operators and functions, at AAM for overlap, lower, upper.
Even more on aggregate functions. Ordered aggregates, hypothetical set aggregates.
Right. Order by inside the aggregate function call matters for some aggregates like string gag or arrag. Hypothetical sets rank within group, let you see where a hypothetical row would rank.
And comparison functions is distinct from for null-safe comparison, conditional expressions, case, coalesce, nullif, database object functions, hastable privilege, peek bat at view def, system info functions, current setting, PG current walls in.
Trigger functions, that's a lot.
An incredibly rich ecosystem built on top of SQL.
Okay, shifting gears. Searching text efficiently, full text search, key concepts, documents, tokens, lexems, preparing text for searching.
Yeah, the basic idea is you process your text documents into a special format, vector, that stores the normalized words, lexems, and their positions. You also process your search query into a special format, script, and the at operator checks if the document vector matches the query.
That's the main matching operator. Functions like tots vector convert text to the vector using a configuration that defines how to parse and normalize words, like stemming running to run.
And tots query converts search terms into the query format, allowing AND or not AV.
Exactly. There are also helper functions like plain tots query, simpler parsing, phrase tots query, searches for exact phrases, web search tots query, understands some web search syntax.
Functions for ranking, rank, and showing snippets, tagline.
Yep. Ranking based on frequency and proximity of matches, and highlighting the matches in the original text.
Postgresql
Helps you see how the text is being tokenized and normalized.
needs dictionaries for stemming and synonyms and configurations to tie it all together.
Right. Configurations specify a parser, how to break text into tokens, and a list of dictionaries, like snowball stemmers for different languages, synonym lists, is spell for morphology, to apply to those tokens. Default text search config sets the default.
And you need indexes for speed, GIN or GIST.
Definitely. Usually GN is preferred for standard full-text search. Create index. Using GIN, MIT's vector column, makes searching large amounts of text much faster than scanning and processing on the fly.
Okay, managing multiple users. Concurrency control. Transaction isolation levels. Read committed, repeatable read, serializable.
The standard levels. Read committed, the default, means each statement sees data committed before it began. Can lead to non-repeatable reads if data changes between statements in the same transaction.
Your repeatable read gives a consistent snapshot for the whole transaction.
Yes. Sees data as it was when the transaction started. Prevents non-repeatable reads, and, in Postgres's implementation, also prevents phantom reads, seeing new rows inserted by other transactions that match your query criteria.
And serializable is the strictest. Guarantees transactions act as if they ran one after another.
Provides the highest level of isolation, preventing even subtle anomalies that might occur under repeatable read in some edge cases. But it can have a higher performance cost due to more locking and potential serialization failures, where a transaction has to be aborted and retried. You set the level with set transaction isolation level lack.
Underneath this is locking. Table locks, but also row-level locks, like for update for share.
Right. Select. For update locks, the rows are returned by the select, preventing others from updating or deleting them, or getting conflicting locks, until your transaction ends. Essential for select then update patterns to avoid race conditions.
For share is less restrictive, allows reads but blocks update.
Exactly. Multiple transactions can hold a for share lock on the same row, but none can get a for update lock. Useful if you need to read rows and ensure they don't change before your transaction finishes. There are also for no key update and for key share, which are slightly weaker variants used in specific cases, often related to foreign keys.
Okay, locks prevent conflicts. Now, how does Postgres decide how to run a query? Query planning. The explain command is key.
Absolutely. Explain select shows you the query plan the optimizer chose. It's a pre-structure showing the steps. Table scans, seek scan, index-only scan, joins, hash join, nested loop, merge join, sorts aggregations.
And it gives cost estimates.
Yes, estimated costs for startup and total execution for each node. Lower cost is theoretically better. Also estimates the number of rows each step will process or output. Invaluable for understanding why a query is slow and how to optimize it.
The planner relies on planner statistics from PG Statistics, viewed via PC Stats.
Heavily. Statistics about data distribution in columns, most common values, histograms, correlation. Without good stats, the planner is guessing and might pick a bad plan.
Which is why running Analyze Zoo or Vacuum Analyze Zoo regularly is crucial.
Essential, especially after loading lots of data or significant updates deletes. Keeps the stats fresh so the planner can make smart choices.
Indexes and query performance are obviously linked. Indexes speed up where clauses.
Dramatically, if the where clause uses an operator the index supports, like or for a B tree, lets Postgres find matching rows quickly without scanning the whole table. Different index types exist. B tree, default, general purpose, hash, only for, STSP, spatial complex types, GN, arrays, full text, BRIN, large physically ordered tables.
Choosing the right index type matters.
Big time. And indexes can help with order by, especially with limit. Sometimes Postgres can just read rows in sorted order directly from the index.
Index only scans, getting data just from the index.
The fastest type of index scan. Possible if all columns needed by the query are available in the index and the table's visibility map confirms the rows are visible, avoids hitting the main table heap at all.
And includey lets you add extra columns to an index just for this purpose.
Exactly. Creates covering indexes to enable more index-only scans.
And parallel query, using multiple CPU cores for one query.
Yeah. Postgres can automatically parallelize parts of queries, scans, joins, aggregates across multiple background workers. Can give huge speedups on multi-core machines for complex queries on large tables. You'll see a gather or gather merge node in the explain plan, controlled by parameters like max parallel workers per gather.
Okay, we need to watch what's happening. Monitoring database activity. PGStat activity shows current connections.
Your first stop for what's running right now shows each backend process, connection, the user, database, client address, current state, active, idle and transaction, the query text if active, and importantly, the wait event if it's waiting for something, like a lock, I/O, CPU.
Wait events help diagnose bottlenecks.
Hugely helpful. Tells you why a query might be stuck.
Other key monitoring views. PGStat statements.
If the extension is enabled, PGStat statements is amazing. Tracks execution stats for every normalized query, call count, total time, rows returned, buffer usage, etc. Find your most expensive queries.
PGStat, database for database-wide stats, commits, rollbacks. PGStat doubles for table activity, scans, inserts, updates, deletes.
Yep. Table stats help you see how tables are being accessed. PGStat indexes shows index usage, scan counts, rows fetched, helps find unused indexes.
PGStat wall receiver for replication status. PG replication slots. PGLocks for current locks.
All essential for monitoring specific areas. PGLocks is key for diagnosing blocking situations. PGStat progress vacuum lets you see how VSUM is doing.
And there are functions to get stats, reset them, dtrace for deep dives.
Yeah, PGStat get functions for programmatic access, reset functions, and dtrace probes if you need super low-level tracing on supported platforms.
Okay, keeping things healthy long-term. Routine database maintenance. Backups covered. And vacuuming. Why vacuum?
Because of MVCC, multi-version concurrency control. When you update or delete rows, Postgres doesn't immediately remove the old row versions. They become dead tuples. VSUM reclaims the space taken by these dead tuples so it can be reused.
And it updates statistics.
Yes, standard VSUM often runs a lightweight Analyze too. It also updates the visibility map, which helps index-only scans. Critically, it prevents transaction ID wraparound failure in very busy databases. It's essential maintenance.
VCUM FIFOL is different, rewrites the table.
Completely rewrites it, reclaiming more space, but requires an exclusive lock, blocks all access. Standard VTON is usually much preferred as it runs concurrently with reads and writes. Only use VCUM flow if you absolutely have to reclaim maximum space and can afford the downtime.
An auto vacuum automates this.
Thankfully, yes. a background process that monitors table activity and automatically runs vacuum and analyze Z on tables that cross certain thresholds, like number of dead tuples. Turnable, but generally does a good job keeping things tidy without manual intervention.
For global apps, localization, using OS locales for sorting, collation, number formatting.
Right. Postgres relies on the operating system's locale support. Collation is key. It defines how strings are sorted. Different languages sort differently.
And you can create custom collations, create collation.
Yes. Maybe you need case-insensitive sorting, or locale-specific rules like German phone book order versus dictionary order. ICE libraries provide lots of options. You specify the collation when creating a database or per column. Also need to consider character set encoding. UTF-8 is usually best.
How do apps talk to Postgres? Client interfaces. PSWAL is the command line tool. Libraries like libqq, C, JODBC, Java ODBC.
PSQL is indispensable for interactive use and scripting. libpq is the underlying C library many other drivers and tools are built on.
What does libpq provide? Functions for connecting.
Yep, pqconnectdb, connect using a string, pqfinish, disconnect, functions to check status, pqstatus, pqmessage,
Sending queries.
pqex, simple query, pqexit, prepared statements for efficiency and security,
Getting results back.
pq result status, pq copals, row count, pq in fields, column count, pq fname, column name, pq get value, get data value as string, pq clear, free result memory. It covered the whole interaction cycle, supports asynchronous operations too.
And finally, ensuring Postgres itself works. Regression tests.
The project runs a massive test suite, make check, make install check, to catch bugs before releases, tests various features, SQL syntax, functions, locales, encodings, uses comparison files and result maps to handle platform differences. It's a huge part of why Postgres is so reliable.
Okay, wow, that was a whirlwind tour of the Postgres 17.4 documentation. We hit data definition, types, server admin, backup, HA, reliability, SQL functions, full text search, concurrency, query planning, monitoring, maintenance, localization, client interfaces, testing. Phew.
We really covered a lot of ground, from the absolute basics to some pretty advanced concepts.
We really hope this deep dive gave you, our learner listener, that shortcut you were looking for, those key insights, those aha moments, without feeling completely buried.
But remember, this was just scratching the surface. That documentation is incredibly rich. If something piqued your interest, partitioning, JSON-B, replication, definitely go read that specific section in the docs.
Yeah, and try it out. Spin up a Postgres instance. Experimenting is the best way to make it stick. What questions did this bring up for you? What are you curious about now?
Think about that. And here's a final thought to chew on.
Okay.
Given all this power and flexibility, we've seen advanced types like JSON-B or ranges, partitioning, robust replication. How might these features change how you fundamentally approach designing and building your next application?
Yeah.
It's more than just a simple database, right? How can you really leverage its potential?
Something to think about. Until our next deep dive.